Hello, welcome to another episode. This week we're going to be covering turbos. So in a previous episode you've seen that I've selected a turbocharged V8 for my unlimited Pikes Peak Racer. And in this episode I'm going to take you through essentially a three-step process of how I came about choosing which turbochargers I'm going to be running in the car. So before we get started, I'd like to ask you all to please like and subscribe. Really helps me get these videos out. And also a few of you have been asking about merchandise. There is some merchandise available and that's on Mountune USA's website, and I've put the link in the description below. So actually before I start on the turbochargers, I'm actually going to say a few things about superchargers. A few people have been asking and commenting about that. Back in 2018, we tried to run a Roadtrek supercharger on the Wolf originally and ended up not going and doing that. There's just a couple big headaches with superchargers for the Mountain. The first one being essentially it takes quite a lot of power to go and run that thing. There's a lot of parasitic loss. Turbochargers do take some power in, essentially a restriction in the exhaust, but nowhere near what a supercharger does. So that's going to essentially remove your crank horsepower, wheel horsepower quite significantly for the same amount of boost. So ultimately you're not going to get the same amount of power out of the thing. And the next point is that it's very hard to adjust boost pressure with altitude. So as you go up in altitude, you want to be putting in a little extra boost there. And that's just a lot harder to do with a supercharger. There's a couple of ways of doing it still, but it's just not as easy and as efficient as going and doing that with a turbo and a wastegate. So we have looked into that in the past. It's interesting, but ultimately turbocharging is the way to go on the Mountain. Okay, step one being selecting the size of turbo. This is a really important thing to go and do, and it really sets up the performance of the car on the Mountain. So with that, the first question I ask myself is, what kind of torque curve and response do I want out of this engine package as a whole? And now I've got a good few years of understanding and development under my belt running on the Mountain, so I've got a good idea of what I want that torque curve to look like. And the things that are important is for the turbocharger to come on as early as possible in the rev range, so having that good essentially spool, so when the turbo starts making boost, that's really hard to get right on the Mountain. And then it's the mid-range torque, and honestly I think that's probably the most important part of the torque curve as it comes to run time, is that mid-range oomph that gets you off the turn. And then finally it's the peak power capability. Ultimately torque's great, but we have gearboxes, so peak power is really where the money is made. So the peak itself isn't as important, but essentially the average power over the usable rev range that you use in the engine in. For instance, on the Wolf was typically running, the peak zone is between 7,000 and 9,000 RPM, and I was typically running the engine between 6,000 and 9,000 RPM. So that's what we're sizing a turbocharger for. Now for this new engine, we're shooting actually for a much broader power band there. I would like essentially the turbo to be switched on by about 6,000 RPM again. And then really the heart of the rev range is going to be more 9,000 RPM up to 12,000 RPM. So you can see I'm essentially trying to broaden the capacity of the engine, requiring fewer shifts, things like that. Tricky task to do, and it's probably not going to be as much as I want, but if you aim for that, you'll get some improvements in that area, and that's really what I'm trying to do there. So knowing that's the curve I want, now I want to go and calculate that. And there is a really useful tool online that I use to go and do this. Borg Warner provide it. It's called their Matchbot. If you literally Google Borg Warner Matchbot, it is the first hit to come up. And that's essentially a 1D simulation that you can put in your engine parameters, and it'll spit out some graphs that you can then align up with essentially their turbo lineup to go and pick and choose your size of turbo. It's been really helpful. I've been using it since 2018 with great success, and honestly, that's a big step in understanding what your engine system's going to go and do. So yeah, go and check that one out and have a little play with it. The other thing I would say for Pikes Peak, and this is a really common mistake I see by most competitors, is smaller is better. Because we think, oh, we're going to altitude and I need to make up for the power loss I'm seeing, people go and pick too big a turbo, and then it ends up just not working on the mountain. I've seen several competitors where they're disappointed because they've gone to a bigger turbocharger this year. I've also done this myself as well. I'm not innocent in this. And then when you go and ask the question, how often are you on full throttle and meeting boost target, it actually happens very rarely on the mountain. The road's so twisty, turny, and the straights are so short. It's rare that you really get a big turbo spooled up to maximum power. And this is why I say you should focus on these mid-range performances more than you are that power number. The other thing to consider is that the top of the mountain is only a small part of the run, and if you're sizing a turbo for that area, then you're going to really struggle elsewhere. And what you're giving up as you go up the mountain is typically not mid-range, but it's peak power. So if you follow other forms of racing, most turbocharged cars run a restrictor, and that restrictor limits the total amount of air that can flow into that turbo. And what that does is that means that you can make peak power very low down in the RPM range because you're unlimited on the torque you can make, and then that peak power stays flat because you've choked the intake to the compressor and you can't force any more air in there. So you essentially end up having torque reducing, RPM increasing, and you keep a flat line of power. Now you'll actually see that power reduce a bit because the faster you spin the engine, the more friction you see, so the net output at the crankshaft is a little less. Also, things like combustion and all that is not as complete. The combustion has to happen more quickly, so you also see a decrease in power at that point. So your peak power is typically the lower on in the RPM range. Well, why do I bring that up? Well, consider on the mountain, because of the air being so thin, you end up turning the intake of the compressor into essentially a restrictor because you're choking the thing. You're getting to sonic speeds of the airflow going into the compressor itself. What people don't realize when they're sizing their turbo, they're just thinking about pressure ratio. Oh, so pressure ratio is the ratio of the intake pressure to the intake to the turbo to what comes out of the compressor. That's that pressure ratio. And because you're starting off with a lower pressure to start with, because of the thinner air, you're going to need a bigger pressure ratio to go and make that same power. Now, also consider on a compressor map, I'll show you one in the video here, it's on one side is flow, one side is pressure ratio. Now, that flow is not a one value, it's a corrected flow, and you correct that flow for different altitudes. So what you end up finding is that the uncorrected flow reduces as the air pressure going into the turbo decreases as well. So that's where you see essentially the peak flowing capability of a compressor decreases pretty much proportionally to the reduction in air density. So just like an engine gets essentially 40% smaller at the top of the mountain, the turbo does as well, and it also has to work extra hard to make the extra pressure ratio. So turbos actually really struggle on the mountain, but the saving grace of them is that they typically have a lot of headroom in them when you're seeing them size for sea level. Whereas what we're doing on the mountain is we're running them to the absolute limit of their life. We're spinning them to the maximum RPM and then controlling essentially that turbo RPM based on boost. So the turbo is being used very differently than what you would see a correctly sized turbo at sea level. So I always say there is essentially turbo sizing up there is Goldilocks. It can't be too small, it can't be too big. If you go too small, you just don't make any power at all. So a lot of OEM turbos suffer with that. They end up, the peak numbers are not very good. But you'll see that actually the OEM cars typically do very well there because it's a well-developed system, and it's still got gobs of torque. And that's where you see something like the Porsche 911 Turbo S, when that did a production car run under 10 minutes, why that was so fast on the mountain. Sure, its peak numbers were reduced, but the response and the drivability was still really good there with the small turbos. And then you do have to, make it big enough, because you need the peak power numbers. Like, you can make as much power as you want, and you shouldn't be leaving anything on the table. So you want this balance of too big and too small, not going either end of it. And what you find is, as you go up the mountain, like at the bottom of the run, you could be quite big and not be an issue, and you can be quite small and not be an issue. But as you get to the top, there is essentially one turbo that is what you need. There isn't much room for variation there. So the reason why I say that, for instance, is you could see it on the Wolf. By the time we got to the top of the mountain, most of the time the wastegate was slammed shut, and we were getting everything we could out of that turbocharger just to keep up there. So the other the other item I go and look at sizing a turbo is previous experience. And we've got a lot of data with us from running the Wolf at Pikes Peak with various different Borg Warner turbochargers. The first year we ran was with, these are all EFR, which is Engineered for Racing series turbochargers. The first year we ran was with an 8474. And that ended up being a little too big, so that was really hard to get on boost and make the power, but once it did, it made a lot of good power. And then the next year, we did something super exciting with them and launched a new turbo with them, and that was the 8370. So that's a slightly smaller compressor wheel, and then a step difference in turbine wheels. So the first two numbers is the compressor size, second two numbers is the turbine size. And that 8370 worked out really well. It's the best turbo we've run on the mountain to date. And that had great mid-range response, and that's where we really learned about mid-range response, and also had good peak power. So we were probably, peak powers around, 600 at the start, maybe reducing to about 520, 530 by the end. So that did really well. And was cool to see, on the release materials for that turbocharger, we had our car on it with Borg Warner, so that was great. And then 2 years ago, I did the cardinal sin of going a little bit too big. We wanted to try out then if the 8474 was too big, and then the 8370 was maybe a little too small, what would be in the middle? Well, that would be the compressor wheel of the 84 and then the turbine wheel of the 70. And so they made us an 8470 against their recommendations, and we ran it, and it just wasn't as good as the 8370. So we learnt that lesson. We hoped that we could rely on the anti-lag to make up for the the bigger compressor wheel, and ultimately we couldn't. And that's why I say turbo sizing is you've got to get absolutely spot on, and all these other systems help, like anti-lag, to get the response out of it, but you can't rely on them. So yeah, that's just something to consider there. And then the other thing to go and consider when this sizing is actually if you're going to go and do a twin turbo versus single. So with the Wolf, because that being a 4-cylinder, single turbo was the way to go. I mean, you could do a twin, but that would be a little silly. Just complexity and weight, and getting the right turbo to essentially run on a 1-liter engine. There's not much available for you there. But with this V8 now, there is a few options around. So I'll go into on step 2 of actually selecting that turbocharger. We do, the first of all, essentially the aerodynamic matching of the compressor wheel, turbine wheel, and you'll see with each brand of turbocharger and different size of turbocharger within the brand, there would be a strength and a weakness to a twins versus singles there. But the thing to also consider is weight and complexity of the twins is greater because you've got 2 of everything. Got to go and support the turbos, you've got to have twice the amount of sensors, all that good stuff. But typically actually packing's a little easier because it sits into the side of the car in a happier place. A big single relies on you running the exhaust pipes to essentially a center point on the car to go and meet that single turbo, and things are a little more asymmetric as well. So that's a lot more of a headache. what you find with the twins is because they're smaller, they spin up a bit quicker. So they're a little snappier in their power engagement. Now, that can be good and bad. I think for, you know, say if you're running a rally car, I think that would be good because typically they're relying on anti-lag and that snap of torque, or you're looking at a circuit car where you can really tune the traction, what you need to the umpteenth amount, you can maybe get a little more performance out of that response. You see that in IndyCar even, they go and do that. But then when you think about an incredibly high powered car that's incredibly light, and that's what we're talking about here, you know, 1,000 horsepower, 1,000 pounds, actually feeding in the power gradually is really, really important. And that's actually quite a different use requirement than say on a circuit. Also consider with hill climb, the road's bumpy, it's slippery, it's cold. What you need is the drivability there. And that's where a bigger single, I think, comes into its own. The other thing you find with a big single is that mid-range tends to be a little bit better. So you've probably got a little more torque capability. Essentially your surge line moves on the compressor map up and to the left. So you have more ability to go and make that torque, which is essentially high pressure ratio, higher flow ratio, higher pressure ratio at the same amount of flow rate, and those lower speeds. So that's a really helpful, important thing there. Okay, so there's some of the basic concepts of what you're looking for in a turbocharger. Now let's put that into reality and go and pick some products. So selecting the turbocharger, the supplier in itself. The first thing I always look for, and I think what anyone should be looking for when you're going and doing this, is actually having good information on the turbocharger. So that's compressor maps, turbine maps. That's so important. And I know a lot of brands don't give you that, and they say our turbo is faster than somebody else's, and it's hard really to go and compare. And I think anybody who's going and making this product should stand behind it with hard data. So that's the first thing I'd say, is go and pick the turbos where that data is available. There's set protocols of how you go and do that testing. It is apples to apples when you go and compare that stuff. So with that data, then you can go and run into the Matchbot or another 1D tool, 1D simulation tool, to go and compare what these curves look like. And I'll share with you the curves so you can sort of see these like estimated power curves. You can do it for different altitudes of what you think you're going to go and get. So that's really helpful in understanding what you think you're going to get out of that particular compressor turbine wheel combination. And the next thing is actually features of the turbocharger itself. So I say that there's a lot of turbochargers available on the market, but there's ones more specifically aimed for motorsport. So you look at, let's say, Garrett series, the G series is just they're great, they're best, most motorsport specific of the retail range turbos. They've got a very high temperature turbine wheel, and that I think it's MARM, and that's good for like 1050C. They also have the best type of aerodynamic, so it's like the most efficient. So essentially you're flowing the most amount of air for the smallest wheel, and then the efficiency number is the greatest, the highest. You also look at, then Garrett has a motorsport line, which isn't available to normal people, but those ones there have very thin compressor housing and very thin turbine housings. So much lighter, less than half the weight. I think some of their turbos in the 3-4 kilo range, whereas typically you're 8 or 9 kilo for equivalent turbo. Some titanium housings even with those as well for the center section, not housing, center section, sorry, titanium center section. But with that comes, if the wheels explode, if you go and overspin that turbo and the wheels break, then all that material is coming through the housing and hitting whatever's in the car. So you really have to do that with caution. And that's why that's reserved specifically for motorsports teams. And then there's other features as well you can go and look at there. For instance, the EFR series has this Gamma TI technology on the turbine wheel, which is titanium aluminide, and that makes the wheel a lot lighter, like half the weight of what you would get with what you're seeing with Garrett. So that really helps with spinning the turbo up. There is some drawbacks with that, like the centerpiece, how that the center shaft essentially. I'll show you here. Here's one I found earlier. Because this material is a bit weaker, a bit lighter, this center shaft is actually a bit bigger in diameter, so that's occupying a bit of space. So overall the wheel, it has to be a little bigger for the same amount of flow rate. But still, I find that's a much nicer turbo to go and drive. And then other factors, things like twin scroll, I think works really well on the Mountune. That's where you have essentially two flow paths into the turbine housing, and that splits out the exhaust pulses a bit more, and that gives more defined pulses on the turbine wheel, and that essentially means that you get a better spool, so you'll spin the turbo up earlier whilst without sacrificing too much at the top end, so the flow rate through it. So that really helps. And the other things I like is the internal wastegate. For my cars, that makes it simple. There's way less plumbing, space is at a premium, and also you can control that really nicely. And then also the integration of a blow-off valve. Again, I'll show you with this EFR turbo. You've got this blow-off valve on the compressor cover, and this works really well because it actually recirculates the air back into the front of the compressor wheel. You can see there's essentially a little groove in there. You might not be able to see it, which recircs, basically air coming out through here, through the blow-off valve and back in there, and that keeps the turbo spun up a bit more as that's releasing pressure because the throttle plate is closed. That's what the blow-off valve does. Also has an integrated boost control solenoid there. So it's got all these really neat features integrated into this turbo. Great. Other thing is this aluminium center section as well, which saves a bit of weight also. But this is a big turbo. This is a pretty big, heavy turbo. But it has a lot of features in it. So when you go and add all that up together, it ends up being lighter than pretty much anything else out there. Once you have the internal wastegate and the blow-off valve, it's getting close to, as a system as a whole, being a similar weight to the Motorsport Garrett setups. It's also water cooled as well, which is nice. Yeah, so I touched on this before, the type package to go and fit in the car. You'll see with this new car, like we originally went for a twins and we went over to a single with the concept, and there's no room for it, but we managed to squeeze it in. So having all these features integrated into the turbo really helps with that. And then the other thing, I touched on this before as well, is then building on what we learned before. So knowing the EFR range really well, we understand, okay, if we go bigger or smaller, what's going to happen. We can compare data we have on the Honda and what we're seeing with the new engine, the Prototipo V8, how that is a little different, how it's the same, and what we'll expect out of this turbocharger with this new engine. So we're not starting from nowhere. We've got a baseline, we know the product range, we know what it's going to do, how it's going to perform, and then we can go and adjust and adapt from there. And then the last thing is actually a supplier I can really trust and rely on. Borg Warner has just been an absolutely fantastic partner to the team. Every win has come with them from 2019 onwards, and I just really appreciate the support they give me and continue to use their product. And with that, so I've actually selected 2 turbochargers for the car that we're going to go and try out, and that is the EFR 9280, which is their biggest EFR turbo, and that will be run at sea level. That's well over 1,000 horsepower capable. And then also the 9274, which is the smaller turbine housing, which will give us a bit better response on the Mountune. And actually an ever so slightly smaller compressor side as well, although the number's the same. The compressor's a little smaller, it flows about 10% less. And that will be for the Mountune. So there are baselines, what we're going to start on. It's probably on the bigger side of things again. I'm not listening to my own advice, but we're going to go and run that on the dyno and see what we get. And that's the step 3, is the testing and the development. So selected these 2 turbos. They're going to go on the engine dyno, and then we're going to go and understand and get some torque curves out of that whole setup. And that allows us to go back into the 1D model, update the parameters, refine what that is, so we've got a better idea, closer idea of how it's going to go and perform, and then from there we can go and see what we got. We can then go and test in the car and see if that matches up dyno to car. There's always a little bit of a difference there. And then finally we go to the mountain, we test altitude and see what we got. And then that's the years of development to see how we do over a season and decide if that's the right turbo and or we want to go and change. So that's the high level philosophy of it. The other thing we can do with testing and developing side is to see if there's some other future developments we can go and do with this essentially as a base. One of the big things that makes a difference is essentially, and I mentioned this before, is the pressure ratio is key on the mountain, and losing the pressure at the intake is an issue, and anything you can gain back is really helpful. Well, you can actually do that with essentially a ram air intake system, and that comes from a really gradual expansion of the intake duct, and as that then goes through the air filter and into the turbo. So getting that designed well and that expanding slowly, you can actually add a couple percent pressure to the flow of the air going into that intake, and actually could be good for 10-20 horsepower, if not a little more on the mountain, if that's done right. Of course, at speed, it doesn't work at 0 speed, but that's actually super helpful, something that we have the space in this car to go and do as well. So that's one of the future developments. The other thing I'm actually really interested in is a variable geometry turbine housing, and that essentially means that we can alter the size or shape of the turbine as the exhaust gases come in. Essentially, the bigger the turbine housing, the more efficient it flows for those large amounts, but it does terribly at the low flow rate. You need that velocity of the exhaust gases to spin the turbo up. So with a variable geometry setup, Porsches do this with some vanes, and then the one I'm talking about here is essentially a twin scroll setup that diverts the exhaust gases at lower engine speeds just through one of the scrolls, essentially really reducing that turbine housing until the back pressure increases, and then you open up both scrolls. That's an interesting development because we're essentially struggling to get the spool and the turbo spun up as well as make the peak power. So I think that just broadens the performance capability of the turbo over the rev range. I think that could be hugely helpful on the mountain. The last thing is actually to go and 3D print some of the the turbine housings, maybe the compressor cover as well, to save a bit of weight. That Borg Warner turbo is about 14 kilo all in, so not too heavy, but there's still opportunity there. That turbine housing itself is about 5 or 6 kilos, so going and doing a thinner one of them, potentially going away from the I think it's the T4 flange, and doing like separated V-bands, which is not an industry standard, but for what we're doing would be helpful. That could save us actually a good chunk of weight there. So a few things to think about, but not essential to get the car running. And getting this car built and running in time is one of the biggest challenges right now. So really focused on that, and understanding we'll develop into the future also. And that philosophy carries over on all parts of the car. So yeah, there you have it. That's how I've selected the turbo for this new car. Couple different options for now. It's going to go on the dyno in the next couple of weeks, and we'll get some results and we'll go from there. But really excited to have shared that with you, and let me know your thoughts and ideas in the comments below. I always enjoy reading them and do my best to reply to as many as I can. Okay, now on to the questions. The first question comes from Play Your Turn to Die ATVG person. It goes, why has he chosen to use a lot of underbody aero if efficiency doesn't matter much and it needs a high ride height? Obviously he knows what he's doing, but I'm pretty confused. Really great question, and you're right to go and raise that. It is counterintuitive what I'm trying to do. So ground effect is the process of having a moving body being close to a floor and that increasing lift essentially, and depending on the angle it increases lift or down force, but either which way it improves the performance of the body. And ground effect is misleading because you think we know that the closer and closer you get, typically you get more performance out of it, which is true, and up to a point, and then it causes issues. Also know that the car, even at 80 mil ride height, is still incredibly close to the ground as it is at 10, 20 millimeter off the ride height. It's just how you go and design that. And then I think ground effect's been talked about most maybe in Formula One recently, where they now have tunnels where they didn't before. They had essentially flat floors before. and we see those cars running a lot lower to the ground. I think of ground effect as, you know, what percentage of the floor is making the overall downforce for the car. Maybe that's a better way of looking at it. And when you have a higher percentage on the floor, that means it's more of a ground effect car, because you're relying on ground effect more to make the downforce rather than the wings. But that can be done at high and low ride heights. And typically when you go from a flat plate, which works essentially much better low to the ground, that's that isn't considered a ground effect floor, but essentially that's what the Wolf was essentially a flat plate at a bit of an angle. That's still using ground effect, but that's not so much a ground effect floor. When we talk about a ground effect floor, so it's more of a naming thing, it's more about this Venturi tunnel. And these Venturi tunnels are actually designed to run at higher ride heights than being slammed on the ground, actually. And you can just alter the geometry of that tunnel based on what ride height or ride heights you want to run it at. So we're designing the Venturi tunnel to be able to work at a variety of ride heights, it not be such a peaky downforce creation system, but it works well at that high amount as well as that low amount. And then what you can do at the high amount, you can also then seal the floor to the ground again with sliding skirts and whatnot. So it's a more efficient way of doing it. Efficiency is always helpful, although it's not as important on the mountain. I also really like the way that the car makes downforce in the center of the car, not on the ends, and that makes it less pitch sensitive, especially when we're talking about this, you know, Venturi shaped floor, which is also less pitch susceptible, whereas like a flat plate, that's incredibly pitch sensitive where that is, so a lot less peaky. So that's why. So in summary, you're talking about a floor, a ground effect floor has a much wider operating window in this case, both in ride height and pitch. And it's still a lot more powerful than overbody wings, so we're going to rely on that to give the best performance of the car and then put the wings on top of that. Next question is from Need a Name Projects. This is a long one, but I read it out. It's a really good question again. It's interesting contrasting this discussion with the engine one. So he's talking about aerodynamics and the and also the engine selection. And I really like this idea coming up here. The amount of development effort that can be stolen from road cars is drastically lower with aero, which is true, going from full cylinder head assemblies down to vague concepts like balanced active aero. So what they're saying there is, you know, we can rely on a lot of OEM technology on the engine side, but aero there really isn't much we can rely on. And really, like, that is true. There isn't much available to us active-wise. There are now some actuators that you could go and lean on, and you're seeing a few, you know, road cars go and do that. But typically, those systems are heavy. And then, you know, like the Gordon Murray car, maybe that keeps the fan. But you can also look at for instance, like the Aston Martin Valkyrie as well. Like all these active systems go away when you look at the race car, you know, and I think that's quite telling. The weight of the system doesn't outweigh its performance. Is typically a marketing tool to go and, you know, sell that car because it does fancy trick things. But in reality, if you're making a race car, you could do a better job with something just dedicated for the track. But what can we do? What can we do to rely on stuff that's already been developed to make essentially it easier to go and develop the aero of the car? And that's where we use sort of known wing profiles. So I use DJ Engineering wing profiles out of the UK, and I've used them on the car for a long, long time. And they're known developed profiles, essentially 2D, so they're consistent over the full width of the wing. And we have good data on them. And honestly, that good data and knowing that they're consistent each time, we don't have to tool them, means that putting that in the right place, in the right operating conditions, is going to get us a lot more performance in developing our own profile. And having, you know, flexibility and maybe different aero packages, different aerofoils is much better than, you know, one wing that does everything, which I don't think you can always do. So that's how we've tried to rely on engineering that's already been done for us and, you know, steal it, borrow it, however you want to call it. But it's a lot trickier to do with aerodynamics. But yeah, this question's a good long one. I won't read it all out, but it is a tough balance to go on. to go and figure that all out. And there's a few things we do, but ultimately a lot of it is very, very custom. Going and tooling the bodywork is also a lot of money. So you can't cheat code everything on the car and borrow other people's parts. And this is one of the areas where it's got to be done right and done by ourselves. That's why I'm putting a lot of time and effort into that. So I hope that answers that question. The last one comes from Carl Condor. How about a reverse DRS that you use to increase available downforce at higher elevations? This is a good question, and the reason why I brought it up here is to essentially say, well, we think about the altitude and downforce a little differently, actually. So it would kind of reframe this question in actuality when we go and answer it. So more downforce is always helpful, but we get to a speed where we can no longer support that. And you know, you would want, especially somewhere like 60, 70 mile an hour, you'd want as much downforce on the car, even at sea level, as you would on the mountain. That's going to help you. And that's where you see with the fan car, essentially. The fan car makes all the downforce at 0 mile an hour, and that benefits from it. But then you have the headache of drag, and then you have the headache of too much load on the car at the higher speeds. And you know, speeds is like the most sensitive parameter to how much force is being made with the car, honestly. Especially when you're talking about a single car with just, you know, like configuration changes. So we would never actually go and run an aerodynamic package trimmed out at the bottom of the mountain and then wind it in. We would probably just run it all the way in as much as we can. And then we would essentially trim it to that reduced amount as we're coming to the suspension load issue. So you've essentially already got an adjustable system. You wouldn't run it trimmed out at the bottom. You would run it all the way in and then reduce its load once you hit that certain speed, and then you would just essentially raise the speed that you'd start trimming out as you went up the mountain, because the load would be, you know, an equivalent load you'd back off at. So you would, yeah, so rather than a system that would, you know, wind in more as you go up the mountain, you would have a system that would wind down less as you go to the top of the mountain. I guess that's the answer to that question. I hope I answered that one okay. Great questions again. Thank you for sticking till the end. Again, please like and subscribe, and I'll see you in the next one. Thank you.